open ecosystem at Intel. You can find us all about us at open.intel.com. We have a wonderful podcast at open.intel.com/podcast as well. Today, I'm very excited to have Ramesh with me on the call. This is our long running series where we have been talking about all the optimizations that we have done in open source frameworks and how they run on top of M7i and C7i instances that are the seventh generation instances in AWS, Amazon Web Services, and they are based on Intel Xeon 4th edition, also codenamed as Sapphire Rapids. So I'm super excited here. Ramesh, hello.
Hi, Arun. Hi.
Do you want to introduce yourself?
Yes, Arun. Hi. I'm a principal engineer at Intel, and my primary responsibilities are for enabling optimizations in TensorFlow. So I work with the open source community and develop optimizations specifically designed for our CPUs and the features that we are adding in our CPUs, and get them upstreamed, working with the open source community.
That is beautiful, actually. So I know you have a presentation here. So
Yes.
let me bring that presentation here and I'll move us to the side. So as I said, Ramesh is going to talk about TensorFlow optimizations. So if you are using M7i, C7i instances, if you are running your workloads, TensorFlow workloads on AWS, this is the webinar that you want to be part of. All right, Ramesh, let's go ahead.
Okay. Yep. Let me get to this. Okay. So many of you may be familiar with TensorFlow. Just to give an overview of what TensorFlow is, TensorFlow is probably one of the oldest machine learning frameworks. It's been around for 6 or 7 years, developed by Google, which they then open sourced in 2016 or 17. It's an end-to-end platform. It provides you the entire set of tools that you'd need to do deep learning, including training and deployment on edge servers or a data or in the data center or even on clients through their TensorFlow Lite framework. It's very, like I said, it's been very popular. Last I checked, more than 700 million downloads, and a large number of developers who are currently using it to develop various state-of-art AI models.
So yeah, I mean, and you're right. This is probably one of the oldest and the most popular framework. And given where AI is heading everywhere, everybody should be like paying attention to what's happening in the TensorFlow world. I mean, 700 million plus downloads is not a joke, really. And
Yeah.
I think one of the points that you highlighted is also that TensorFlow is used for inference and tuning and training. Is that right?
Yes. It has end-to-end features. Yes.
And it works across CPUs and GPUs and a lighter device, Tensor Lite, for example, that you talked about.
Yes. CPUs, GPUs, accelerators. For example, this is one of the supported frameworks for the Google's TPU accelerator.
And likewise, like when we launched M7i C7i, as part of that, we have a couple of a few accelerators as well. And as part of those accelerators is what we were talking about. That one of the accelerators that you intend to talk about is AMX. So let's hear it.
Yes. Yep. Yeah, like Arun said, AMX is the one of the first or the latest accelerators that we've added in the fourth generation Xeon, also known as Sapphire Rapids. So basically, this accelerator uses
So
a
actually, Ramesh, if we take a step
yes,
back, for
yeah.
people who are using M7i, C7i, what does an accelerator mean for them? Is it like a additional card? Is it additional area in the CPU? Is it on the chip? Is it something that they need to do to enable it? What is an accelerator? Help us define that.
Yeah, for an end user, data scientist or someone deploying, they they don't even know it's there. It's just automatic, right? So this is a new set of instructions that we've added in the CPU, and working like my team and several others, we work with all the framework vendors to just make it automatically work, right? So the end user doesn't even know it's there. They're just going to get the benefits of using their running their models using TensorFlow, on a M7i or C7i.
So you have the CPU, which is doing crux of your processing, but in
Yes,
addition, there is these additional instructions which
Yes.
can get triggered where
Yes.
the tuning or inferencing could work in a much more optimized manner.
Yes, yes, yeah. So, for example, for like I said, this is a new set of instructions. So the difference between these instructions and what we had previously is that these instructions work on matrices, right, rather than vectors. And so what happens is you can, use these instructions to compute, larger amounts of data. For example, larger matrices you can compute with just one single instruction. Right? So what happens is that because you can do so much of additional matrix multiplication using one instruction, um, typically in AI, you have AI is mainly based off lots of matrix multiplication, large matrix multiplication. So you can then divide the workload into smaller chunks, and each one that fits into an AMX instruction, and then in parallel issue AMX to the multiple cores on the platform, and that's how we get to take full advantage of all the parallelism in the CPU.
So the
And
parallelism is the one that actually makes the processing instruction go faster because you have taken a big chunk, broken down into multiple smaller chunks, and you're parallelizing that, and then you gather that data back and then get the results.
yes, that's right. Yep. So we use the AMX capability that itself can do multiple, multiplications at the same time. Thousands of matrix multiplications in one instruction. Plus, we have the cores, right? The large number of cores, so they can provide some additional parallelism um, for doing the matrix multiplications.
There's really the combination of the parallelism here and then leveraging that, tying that to the core is what is really increasing the ability to do this. And when we do inferencing or fine tuning, these are all end of the day matrix multiplication. And with AMX, that's how we are accelerating it.
Yes, that's right. Yes.
Okay.
Yeah.
And
And
the bottom bullet talks about something about B float 16 and int 8. What are these data types?
yes, yeah. So to fully utilize AMX, you need to use a different data type. Normally, most of the models are created using floating point 32, which is 32 bits. But AMX supports a smaller precision. The two precisions that it supports is B float and int 8. B float is a 16-bit data type, and int8 is a 8-bit data type. bfloat is used for both training and inference, but int8 is specifically designed to do faster inference.
And so these are native data types in TensorFlow?
Yes, they're all both are native data types in TensorFlow. So let me quickly jump to the next file, give a little bit overview.
Wonderful.
Um, yeah, so both are native data types. They're supported by TensorFlow as well as other, frameworks like PyTorch. So I won't talk about int8, mostly focusing on bfloat for today. So bfloat is, as I said, 16-bit data type that was first introduced by Google in their TPUs, and they have added that support as a standard data type in TensorFlow. And what we did was we extended TensorFlow to so you're able to use the same data type on CPUs along with AMX. So the difference, there have been other data types, for example, the floating point 16, which has been around for a while, but Google introduced this. It's slightly different from the format for an FP16. So it uses the same 8-bit precision as the FP32, right? So that's very advantageous in machine learning. And that's one of the reasons why they introduced this data type rather than using FP16. So we in AMX, this is the first acceleration. We choose BF16 for acceleration. The advantages, these are 16 bits, right? So you use less memory footprint. So all your weights, which are basically half right now. It allows for higher bandwidth, and more importantly, you can do more compute per cycle compared to FP32.
So I think the point that you mentioned over there is because end of the day, when you're doing, inferencing, you're looking at sort of what the model weights have been based upon which you do the inferencing, and that's what you're tying here. Because with the 16-bit data type, you can do more weights and it gives you better precision?
The precision will be the same as, so if you use bfloat, some of the experiments that we have done, your precision is very similar to FP32, right? So just because your models are in a smaller data type, it doesn't really affect the accuracy. Right? So for training and for inferencing, you will see very similar accuracy to what your floating point 32 models provide. Yeah, so
Right.
it's basically you get things for free, better performance for free.
Correct, and less memory footprint as well. So
That's,
there's a lot of concern around so much AI happening. What kind of carbon footprint it happens? So the more we can conserve on that side of the world, the better it is.
yes, that's right. Yep. Yeah, the
And
models are getting
the other
bigger,
part
right?
I
They're
also realize it is in terms of creating LLMs. Now, only so many companies can create LLM because it requires massive investment. And then comes fine tuning, and then comes inferencing. There are so many there are so many end user customers that are going to do inferencing, and that's where Intel CPU with AMX accelerator would shine. And only so many companies can create LLMs, but inferencing is a lot more. So that's where these data types would be very relevant.
yes, that's right. Yeah, yes. So
Okay.
if I go to yeah, so now the question is how do you use it in TensorFlow, right? So you're a TensorFlow user, you have models that are in training and deployment. How do you use that? The good news is that all the MX support is automatically in the official PyP package. So pip install TensorFlow, the latest TensorFlow, you get everything. And you just need some minimal changes in your code to trigger to let the model or to let TensorFlow know to run the model in bfloat. And you need some minimal code changes. They're typically one line. Here's an example for if you're using a newer model, just one line, set the precision. And if you're using some of the older models like TensorFlow Hub, they use a different backend. So you need a different setting, again, a single line. So just single line, no changes, same default PyP packages. You should be able to utilize AMX. So the code changes that we've upstream, actually looks at the instruction set. And if you have AMX, then automatically it'll route all the large matrix multiplications to the AMX unit or the TML unit for optimizations. Everything is done seamlessly.
And what if the AMX is not there?
Yeah, if you AMX is not there, then we suggest not to use these switches, because when if AMX is not there, we try to run the model, so that they don't lose much performance. But you're not going to get anything. You're not going to get any benefits
Well,
from
because
using this.
but the customer may not have control over whether AMX is enabled or not. So, I mean, think in a classic DevOps environment, the dev are kind of creating these models, and they don't know where it's going to be deployed, which CSP is going to be deployed, and whether the CSP is going to enable that accelerator or not. So, what is the recommendation in that case?
Yeah, ideally you should not, just check the CPU, and if it's one of the later generation CPUs, you can actually not use this. But even if you use this, you may see a small performance drop, but you won't see any gains. So if you probably should just give a quick test. If it does work well, you just leave it. If not, just disable the settings to
And
get
that's
the
a
best benefit.
wise advice, because end of the day, no matter what the benchmarks say, what the code says, what the documentation says, you got to see what works in your environment you are setting.
Yes, yeah,
One more point I want to
ideally.
highlight, as you mentioned in the very beginning, pip install TensorFlow is straight up in the upstream package. There is nothing fancy required there, right?
Yes, that's it. Yep, that's all that's needed.
Okay, wonderful. And I think you were trying to say something. I might have spoken over you.
No, that's what I was saying.
Okay, awesome. All right, let's keep going.
Okay, so I mean, just how the flow is, right? So if you like Arun mentioned, fine tuning and inference are some of the two places where people are using CPUs, and the Intel Xeons are highly suited for those kind of workloads. So if you're doing fine tuning, so what you do, again, not a lot, just set the FP16 precision, and run your model. That's it, and use FP16 for training, and then when you're done, the weights will be stored back in FP32. So the reason we stored back in FP32 is you can then run it, like Arun said. Some instances may not have AMX, so you may not get a lot of benefits. So it might be just better to run them in FP32. So we just store them back in FP32. If you're doing inference, you have a couple of choices. Like I said, we support int8 and we support bfloat. So if you're really worried best performance, you can use an Intel neural compressor, which converts all the weights into int8, and then use a framework like TensorFlow, and again, you'll get the best benefits. But if you can,
give us a line about Intel Neural Compressor. What is Intel Neural Compressor?
Yeah, Intel Neural Compressor is a tool that we have that basically takes your model and pre-processes and converts it into int8. So it's even more compressed than bfloat, right? So it's basically your weights can be 32 bits, and if you bring them down to int8, it's actually 1/4 the size. So you get even more compressions. But you do have to sometimes trade off some accuracy because so that's why you have to make a choice between do you want something that's highly accurate or you want something that's very fast. So you make
really
the
have to
decision.
figure out whether you want to eat the cake or you want to have the cake.
Yeah, that's a good way to do that. Yes, yeah, you can have both same. That's right. That's a good way. Yeah.
Okay, but ultimately, once you have your optimized model, whether for speed or for space, it runs back on the 4th gen Intel Xeon, in this case,
Yes.
m7i, c7i.
Yes. Yep. Yeah. You just use the optimized frameworks like TensorFlow, and you run it on a on a process that has AMX, and everything is done automatically. Right. There's nothing extra that you need to
Got
do.
it. Okay, that's beautiful.
Okay, so let me try to show a demo of
All right.
AMX running on a c7i. Let me see if the demos work well. Okay,
Okay,
so
let's give. Walk us through the demo setup. What is the demo setup here?
yes, so let me see if this is still alive. Yeah, it's still alive. So this is I created an AWS instance on a c7i 12x. So that's a 48 vCPU instance. And if I do an LS CPU, so it'll tell me more about the platform. So it's a Sapphire Rapids, 48 cores. The key thing that you need to look for is the whether AMX is enabled. So you can see that the set AMX style, AMX int8, AMX bfloat are all automatically
So that tells
enabled.
you that is not just running Intel 4th Gen Xeon, but it also has the AMX accelerator enabled.
Yes, that's right. Yeah, that's one way to find out whether AMX is enabled or not. Yeah. Yep. And I have a Python environment set up and everything
And this
installed.
this C7i instance is running Ubuntu, it seems like, is it right?
Yes, yeah,
And that's
it'll
again
be
stock
running.
Ubuntu.
Yes, Ubuntu 2204. Yes.
So just stock Ubuntu that customers would have access to. Nothing
Yes,
nothing
stock.
customized here.
Nothing customized. Yep. When I created the instance, I just picked Ubuntu 2204. That's pretty much
Okay.
it. Yep.
Okay.
Yep. And I have a Python environment set up. I think, let me see, it is Python, it's Python 310. Okay, so what I'm going to show is a demo now of a object detector running. So let me. In my thing here, I have a Jupyter notebook. Jupyter notebook is one of the popular way for people to develop and debug, Python code. So I have Jupyter notebook running there, and then I have my browser connected to that.
You have a pipe
And
set up on your local machine by which you can say
yes.
localhost 8088.
Yes, and it just runs it on the instance. Yes.
Got it.
So let me open this up. So this is one of the examples that I got from the TensorFlow website. One of the examples to do object detection. So you give it an image, and it finds all the objects and draws some nice boxes around it. The original code is here. If you link there, you'll get to it. So let me just quickly walk through you this. I don't spend a lot of time on this. So it's basically, setting up, it's setting up some functions that will download the image, setting up some functions on how to draw the boxes. And here's the sample that it's going to use. These are just preview. It's not run it. It's just preview of the thing.
Right.
And here's the key thing. So this is the TensorFlow code to get a specifically pre-trained model. We're going to do inferencing. So it's a pre-trained model. And this is the code to run the detector. And here is what it's going to do is run the detector. So what I'm going to do is I'm going to run it up to that point, right? Let me run. Okay. So this is going to be running this. So the stars says it's still running. You can see the stars there. So where is it?
The star in Jupyter Notebook means it's running.
Yes, yeah. So 4 means if it has a number, it's done. Yeah, it's running here right now. Right. So let's see when it comes to the. Yep, it's just. It takes a little bit to set up and run.
That's fine. That's fine. But just to kind of reiterate, this is c7i stock instance started from AWS, where you did set up a Python environment and you did pip install TensorFlow, and you're using a Jupyter notebook that is actually leveraging that TensorFlow environment now.
Yes, yeah. Yes, so if you can see, it's just printing some messages. Let me do while it's doing that pip list. Yep, see, it's got all this, just standard TensorFlow, 2.15.
Beautiful.
And some TensorFlow things. So let me go back to let's see if it's got through that. Yep, it's got through all of those, right? So it's just ready to run this. So what I'm going to do is, so I need to run this for a few times because the first time it takes a while to run.
Yeah.
So I'll just run it for 5 steps. Okay, and then let's run this. So it's running right now. The first time it takes a little long because it has to download the model and set some things up. So you'll see.
And I can see number 9 already.
Yeah, this one is still running.
That one is still running.
Yeah.
I see.
Yeah, so it's reading the graph and doing some setup. Yep, you can see that it's running right now. So the inference time took about 23 seconds first time, but subsequent times it's all very fast, right? 124, 125.
Yeah.
And here's the output, right? It's probably identified a few things, a table, some chairs, identified a tree.
Yeah.
Okay.
Umbrella,
so this
maybe,
is, you have quite a few things it seems to have identified.
So this is a stock TensorFlow example that we ran. And what did we do in this TensorFlow example to ensure that this is running on AMX?
No, right now I'm showing you it's not running. So
it's not
using AMX. It's not using AMX.
Okay.
So now I'll show you how to use AMX, right? How easy it is to use AMX. So let me go then kill this, shut this down. Go back. Probably I should just save this so I can save the notebook, and then I can shut this down and I'll restart it and run the AMX.
Got it. Okay. So you're really truly showing before and after.
Yeah, before and after. You saw that, right? So if you look at it, it's taking about 1.2 seconds or so.
Yeah. First was 23 seconds and 1.2 seconds, and let's see what magic can AMX.
Okay, so now how to add, right? So there's some good documentation we have that walks you through how to add. I'm going to quickly jump to the TensorFlow Hub because we're using a TensorFlow Hub model, and this exactly tells you if you're doing TensorFlow Hub, what do you do? So all this is just needs one line of code. Like I said, and let me copy that.
So yeah, I got it. Okay.
Let me copy that, and let me edit this. So as soon as TensorFlow is loaded, I'm going to say, okay, you're going to run and we'll do the same thing. So that's that added. So let's do the same thing. I'm going to run up to yeah, at this point. So the log from the previous one is still there.
Right.
So let me run up to, okay. So it's going to start running
Yeah.
these.
Yeah. And now it is explicitly enabling the program to run on AMX because of the line that we put in.
Yes, yeah. So it's gone through there. Okay. Fingers crossed. Make sure the demo cards work this time. So, okay, it's still doing that, and now you probably should provide. It'll give you some messages saying that it's converting the model into B float. Let's see that.
There you go, 5, 6, 7. Okay.
7 is done, right? Yep. I think it's now waiting for you. So let's run this. It's running. Yep, you can see the model. It's right now. You'll see this message. It's converting the model into B float.
Right. There you go. Yeah.
Yeah, TensorFlow seem to be very, chatty. It puts out a lot of messages. Oh, here's the stuff. So you can
Oh,
see the first time
really?
it take 26. Yep, 60 seconds, 600 milliseconds, or 0.6 seconds.
That pretty much cut down the time to less than half,
Yeah,
actually.
yeah, less than half. So I have the original one. You can see
Yeah.
1.2, 2 point, right?
Right.
So you can see, and then you can see the same objects got detected.
Right.
Table, chat. Um,
And if you think
yep,
about it, your
yep,
initial inferencing could take time, no matter what,
yeah,
but you are more likely to do repeated inferencing, and that's where if you're saving 50% of the time, that's massive, actually.
yes. Doing nothing, just one line of change, right?
That's it. That's it.
Yep.
Fantastic. Oh, what a beautiful demo. So let me
Thanks a
repeat.
lot.
Let
Yeah.
me repeat.
Okay.
C7i, Ubuntu stock TensorFlow example. We made one line change because we were running from TensorHub, and we saw our inference timing dropped by about 50%.
Yes.
And again, this could vary, for different use cases based upon what you're using, but that's what we
Yeah.
just saw.
Yes, that's right. Yeah, it could vary based on your use case. Yes.
Yeah, yeah,
Yeah.
yeah. No, that's fantastic. Okay, awesome. Cool. Okay, what else we got?
Yeah, I think just a little bit more, some benchmarking. So we have an Intel model zoo where we have a whole bunch of, popular models like BERT, ResNet. Routinely, we go and optimize these and make sure they're all well optimized for AMX. So just to give an example that, what you saw in live demo, we've have the same, optimizations running in the model zoo. And here are some examples where you can get even larger benefits on some of the models. For example, BERT, we were seeing about 2.7x improvement. Again, and for Resonant 50 inferencing, these are all inferencing. We see about 2.45 improvement, all running on c7i, 12x large, which is a 48 core,
And that's exactly what
48
we
vCPU.
use in our example as well.
Yes, same thing what we use
Yeah.
in
And
example.
in our case, I mean, basically what we saw was a 2x performance improvement, essentially.
Yes, yep. There we got there we got 2x. Yes, that's right.
Yeah. It cut down the inferencing time from 1.2 to 0.6.
Yes, 0.6. Yeah, it take 1.2 seconds. Without if you just run it, and don't use AMX, and if you just use AMX, it cuts it down to about half the time. 0.6.
Beautiful. Okay.
Yeah.
All right. And is that the last slide as
Yeah,
well?
I think that's all I had.
Oh,
That's all I
beautiful.
had.
Okay, so let me hide this here. And so, Ramesh, I really enjoyed this. What is your
Thanks a lot.
recommendation for the developers that are getting started with C7i and want to use TensorFlow?
Yeah, I think they should first, enable AMX, right? It's just right out of the box. There's lots of documentation. I showed you one where Intel we kind of explain how to use it. It's just one line. There's also documentation on TensorFlow.org. You can go there, and it's just easy to use. They should start, using it, and why leave performance on the table, right?
Yeah, exactly. I
Yeah,
love that line. Why leave
yeah,
performance on the table and throw more money? That no, I don't
yes,
want performance gain, because performance gain is actually saving money essentially. So, and that's maybe an appealing message not just to developers, but to the executives as well.
Yes, yeah.
Where people have questions, where can they find you?
I'm on LinkedIn and I'm on Twitter. My handle is agramesh13 on Twitter and agramesh on LinkedIn.
And
Um,
are you also on the TensorFlow community Slack channel?
yes, yeah. I think you can. Yeah, you can. They can even post on TensorFlow GitHub questions on and issues. Um, yeah, I think that's also another way to reach out to us if they have questions.
Got it. Okay, fantastic. Thank you. Well,
Okay.
thank you, everybody. I hope you enjoyed the webinar. Uh, if you're using C7i, m7i instances, if you're using TensorFlow over there, make sure you're leveraging the AMX instructions. As Ramesh said, why leave performance on the table? We have done the work. You just have to use that a line or two to extract the best out of the C7i, m7i instances. All right. Thank you, everybody. Bye-bye.
Thanks, Arun.
Thank you. Thank you,